All right, let's go ahead and get started with lecture 19. And today we're going to finish up our whole discussion of why we're talking about the discrete Fourier series, its relationship to the discrete Fourier transform, and several important concepts that we're going to use kind of throughout the course. Right now we're trying to get under the hood of the DFT because the rest of the course is about how to apply the DFT. And if you really understand how to use it and what it's doing, it makes it quite a bit easier to make things more efficient. So the first important concept that we have to cover today is periodic convolution. Now, we talked a lot about convolution in chapter 2, and you got some practice doing that and running the exercises there. And the bottom line there was it's great. If you have a linear time invariant system, you can convolve it with an impulse, any input with an impulse response, and you have the output. Okay, great. What is periodic convolution? Well, I'll steal thunder from the upcoming lectures, but as it turns out, to implement any convolution efficiently, you're probably going to use DFTs or FFTs of some sort. If you do that, the FFT doesn't implement linear convolution. It implements periodic convolution. So what does that mean? That means you have to adjust your implementation of the FFT so that the periodic convolution that it does accomplishes your intent of linear convolution. So that's the reason why we care about periodic convolution, and we'll discuss that in some detail next. So with that in mind, we're talking about periodic sequences for now. And if we've got basically two periodic sequences, we'll call them X1 and X2. You can see this looks very much like our, whoops, not K, but a 2. We've got two periodic sequences and two discrete Fourier series. So discrete Fourier series, discrete Fourier series. And we synthesize, or I shouldn't use the word synthesize, we make a third sequence, X3 of K, which is just the product of these two. So we've got this set up, and you've seen this before in chapter 2 where everything was Fourier transforms. Then, in the case of the previous material, it was a linear convolution, and this time it is a periodic convolution. And X2. So let's sort of try to start unpacking this periodic convolution. So first, it's a sum over a finite interval. So finite interval, why? Well, it's a periodic sequence, and we're just going to use one period of the infinitely long sequence. And so the period is n. So we're going to do it over a finite interval. And so the key thing we're going to talk about today, we're going to get into some detail, maybe excruciating detail at first, and then build up your intuition, and then we'll start being efficient. But the values of x tilde of n minus m are in the interval 0, m, n minus 1. And that is basically a reminder of last time when we talked about, well, what is x of minus m in the context of these periodic sequences? And remember, we had to interpret that minus m, that index of minus m, in the context of modulo n arithmetic. And so that required a little bit of, that's where I generated that table to try to show you what was going on. And then finally, once we do it once, we just put ... and we repeat periodically. for m outside 0, m, n minus 1. So it's kind of our ground rules to get started. And to sort of make this more concrete, we'll do an example. So let's generate two toy sequences to play with. In our example, we'll make n equal 4. And so x1 is going to be 0, 1, 2, minus 1. And then dot, dot, dot on both sides, because this goes on and on, and just repeats. So if it's not totally clear, you can think the next sample over is 0, 1. So it's just a repeat, forwards and backwards. So that's x1 of m. Let's take a look at the second one. That'll be 1, 2, minus 1. Minus 1, 0. One, 2, minus 1, 0. All right, so what we're going to do is try to convolve these two sequences together and go through a process that's a little bit lengthy and detailed at first, and then we'll build up some intuition, and then hopefully that'll help you be able to do this as efficiently as you do the regular linear convolution. So if we set that aside, so what's the output? Well, it's this third sequence, and if we just start with the equation, x1 tilde of m, x2 n minus n. So our first order of business, let's start with 0. That's at the beginning and should be easy, right? And we did something like this last time. So if we attack that, we end up with an equation like that. So we're going to be summing everything, m equals 0 to n minus 1, multiply these, and we're good to go. So we already know what x1 of m is in this interval, 0 to 3. So we're set there. We don't care about that part. So the question we have to ask ourselves is, what is this? And so what I like to do when I'm trying to explain this, or first get comfortable with these ideas, is make a little table to kind of keep track of things. Now, m is our index, and we're summing over that. And everything, our entire world, lives between m equals 0 and n minus 1. So that's step 1. We know, luckily, what x2, if I can write x2 of m is, tilde, that's given. And so we can go back to our plot and say that's 1, 2, minus 1, 0. So far, so good. Then I usually like to put this minus m in there. Well, minus m is just 0, minus 1, minus 2, minus 3. Very straightforward so far, but we're in modulo n arithmetic, right? So it can't really write it like that. We have to write it, oops, m is 4. So what does that mean? Anything that does not fit between 0 and n minus 1, where n is 4, so n minus 1 is 3, has to be wrapped back into that. And how do we do that? We either subtract n or add n so that everything falls between 0 and 3. Well, we care about minus m, and minus m has these values. Well, 0 is between 0 and 3. So check, that's good, no problem. Minus 1. Minus 1 is not in the interval, so we have to wrap that. So we have to either add 4 or subtract 4 until it lands in the realm of 0 to 3. So hopefully it's clear that if you subtract 4, it's negative 5, so we're going the wrong way. Things are getting uglier, so we add 4. 4 minus 1 is 3. 4 minus 2, so we add 4 to minus 2, you get 2. 4 added to minus 3 is 1. So far, so good. So now we're going to say we've got our indices. Now I'm going to write it as minus m mod 4. So now what am I? Now this is where things get just a tad more subtle. I'm going to take those indices and use them as the argument for this x2 tilde, because that's what I care about. So let's carefully do that. This minus m of 4, the very first value is 0 here, right? So x2 tilde of 0 is what? Well, there's x2 tilde of 0. Put in 0 there, I get 1. So 1 is the first entry. We go to the next one, 3. So x2 of this minus m mod 4 is 3 in this case. So x2 of 3 is what? We'll have to go over here and find 3. x2 of 3 is 0. And that's why it's a little bit intricate, because things are kind of out of order depending on how they wrapped. So it's kind of good the first few times you do this to go a little slow and try to follow along. So we're just trying to fill in this table of what things look like. So we'd go to, 2 is our next one. And so 2 is the index into this. What is the value of x2 tilde of 2? Well, luckily I already wrote that down over here. When 2 is the argument, x2 tilde is minus 1. Right, and our final one is 1. When m is 1, x2 tilde of 1 is 2. So going kind of the long way, we've got our expression here. Now what are we going to do with that expression? Well, we already said we're just going to multiply it times x1 of m, right? And so when we do that, sometimes it's helpful, I think. Since we have the room, why not just write it down? Yes?
Sorry, you called it mod 4?
Yes. Modulo 4.
Oh, modulo 4.
That's what I meant, not modulo 4.
Oh.
I think that's what the book uses, the same terminology. So everything exists between 0 and 3 if you're modulo 4.
Okay.
So what if it's 0 to 4 and modulo by 5?
Right.
Oh.
Right. If it's modulo 4 if it's modulo 4, everything exists between 0 and 3. Or modulo n, as they say, then everything exists between 0 and n minus 1.
So for x2 till the modulo, the thing, it's not only by flip it, but it's not flip it, but like choose random, not randomly, but the order is
It's out of order. Right.
out of order.
And maybe what we'll do is we're going to plot this too, so you can kind of see what's happening, because there's a generalization of this that we're going to go through this table like 3 times, and hopefully it'll get into your system of how it works, and then we're going to plot them, and you can see that in fact things just keep wrapping is what happens. In the old convolution, we kept moving the thing to the right as we moved along. This time we're just going to wrap it. It's just going to rotate. Things are going to shift out and around and back in on the left. And you'll see that. But we're going to go through the mechanics so you can kind of see what's going on under the hood, and then you'll feel confident to be maybe a little more efficient later. So since we're going to multiply this x2 times x1, I'm just going to write down the values of x1 here in this other column. And I know I have those from our original problem statement, 0, 1, 2, minus 1. So I'm just going to write down 0, 1, 2, minus 1. So now with this little table to help keep me organized, I can say, well, this x3 tilde of 0 was the sum, m equals 0 to n minus 1, which is 3, x1 tilde of m, which is readily understandable, times this x2 tilde of minus m, but we know minus m is really this modulo 4 thing. When I write, hopefully that's not confusing, when I write minus m here, it's kind of goes without saying that it has to be modulo 4, because everything exists between 0 and n minus 1. And here I'm being more explicit to just sort of remind you that, hey, we went through this trouble making this table. Now I can replace everything with this entry here with everything in this entry there in this table to make it easier to just, kind of turn the crank as you get started with this. So that should make it easier. Now we can say, all we have to do to just mechanically function here is with m equals 0, x1 of 0 is 0 times x1 of, let's see, did I get that right? 0. Let's see, there's something. Yeah, that's right. x1 of 0 of this, which is 1. Plus, then I put in m x1 of m, which luckily I made this label here, so x1 of 1 is just 1. That's a little bit confusing. Times x2 of minus m. And what's m? M is minus 1, so minus 1 mod 4 is right here, right? So that puts us at 0. So if we work our way across, and now I'm just writing basically the products. Everything in this line here is just the product of these two columns. And the intent of designing this table was at the end, all we had to do was multiply these columns together. So 0 plus 0 minus 2 should put us at minus 4. So that's our first output. Let me set this aside because we're going to come back to it. All right, let's do another one where now we're going to let n equal 1 before we let n equal 0. And now you're going to see what happens with n equals 1. So we got x3 of 1 now, and we're just plugging it into the equation to get kind of set up. So we've got x1 tilde of m and x2 tilde of 1 minus m, because n is 1. So this is the problem we're trying to address. So now with that set up, let's make our table again. Things will be somewhat similar with a twist. So we've got x2 tilde of m, same as before, 1, 2, minus 1, 0. But now what do I care about? Now I care about this quantity, x2 of 1 minus m, and of course that's modulo 4. So I'm going to just write down 1 minus m. And I do this to kind of keep me sane so I won't have to do it in my head. What is 1 minus m modulo 4 all in one step? Because I frequently mess that up. So easy, 1 minus 0 is 1, 1 minus 1, 0, 1 minus 2, negative 1, 1 minus 3, negative 2. So you can see this is where the fun starts, right? So 1 minus m modulo 4, just like before, the entire world must map between 0 and 3. So if I throw 1 in there, well, 1 is between 0 and 3, so good to go, don't worry about it. Same goes for 0. Minus 1 is a problem again, so minus 1 plus 4 is 3, and minus 2 plus 4 is 2. So luckily everybody's accounted for, everything maps between 0 and 3. So now back to, we have the indices, or the arguments of x2 of n. Now what is the actual value, right? So we'll make a column for that. So x2 of 1 is what? Well, there's x2, there's 1, they meet at 2, so that's correct. x2 of 0 is, well, when m is 0, x2 is 1. This is 3, so x2 of 3 is what? Go over to m equals 3, x2 of 3 is 0. Question? Let's see, do I agree with this? 2, 1, 0, minus 1. Yep. And the last one, x1 of 2, m equals 2, we got minus 1. So we're good to go. So now let's just for our own convenience, we can write down the values of x1 of m again, which of course haven't changed. It's x1 of m is always the same, right? So 0, 1, 2, minus 1. So now we're at x3 of 1. We can just multiply these together. 2 times 0, 1 times 1, 0 times 2, plus minus 1 times minus 1. Maybe I'll put a parenthesis, make it easier to see. Just multiply these two columns times each other. So that comes out to be 0 plus 1 is 1, 0 minus 1. I don't think, wait, minus 1 times minus 1 is plus 1. That's my problem. 1 plus 1 is 2. Good. So what we're going to do next is one last one of these tables, and now we're going to put all these, we're going to plot every single one of these x2s that have been shifted and compare them. And you'll see that, yep, you can go through this table if you want and see what's happening, but you can also do something very quickly, which is just rotate it and shift each time, and then you're back to where you were in chapter 2 if you were doing linear convolution. So let's do our last one and then draw our conclusions. Let's see if you can see the pattern kind of emerge from all this. So our last one is we're going to let n equal 2. So x3 tilde of 2, 0 to 3, and x2. And well, that's 2 minus m. Of course, everything's modulo. So let's go ahead and fill that out. So let's see, we'll start with m. That's pretty easy so far. Same as before, 1, 2, minus 1, 0. Now we've got 2 minus m. So now things are different. So 2 minus m is 2 minus 0 is 2. 2 minus 1 is 1. 2 minus 2 is 0. And 2 minus 3 is negative 1. But as you are very well aware of now, we live in a world between 0 and 3. So we've got to check all these to make sure they're modulo. And all those are fine. Minus 1. Have to add 4 to that to get 3. And then finally, we have to go evaluate, well, what is all those values now that we've computed modulo 4? So x2 of 2 can come over here to my x2 column, find 2, write down minus 1. x2 with an argument of 1 is what? x2 argument of 1 yields 2. Next value is 0. x2 of 0, that's easy, it's at the top. x2 of 0 is just a 1. And our very last one, x2 of 3, it's at the bottom of the table, that's easy. When m is 3, x2 is 0. And then just to make our lives very easy, we can just recopy this down. And now we just multiply these two columns to get that final answer. So let's see if we can fit all this on one slide here. And say x3 tilde of 2 is minus 1 times 0, 2 times 1, 1 times 2, and 0 times minus 1, which should be that's 0, that's 2, plus 2 is 4, 0 again. So x3 tilde 2 equals 4. So that was a little bit, a long way of doing it, as it turns out, with these tables. But I wanted to do that so you could kind of see, maybe in a more organized fashion, what's happening. And now we're going to go back and just look at what's happening from a graphical viewpoint and see if you can, kind of see the pattern and adjust. So let's put it all on one slide here, because we need lots of room. We're going to try to put all the plots here so you can see everything. So back before, when we were doing linear convolution, I always like to write like the first sequence up there and then shift the second one that was shifting. If it was, h of n minus m or whatever, we would just shift it across. So the first one was kind of held constant. And so I'm going to write x1 of m as sort of the thing that's not moving. And we've got what? 0, 1, 2, minus 1. And dot, 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 because everything's periodic. Sure. Now, let's look at x2 of minus m. So I'm going to go back to this sheet here and look at x2 of minus m. And these are the values, right? And I'm just going to write those values where they belong, which is on every single one of these indexes, m, 0, 1, 2, 3. I've got this, 1, 0, minus 1, 2. So I'm going to plot that on here. So the first one is 1, then I've got a 0, followed by a minus 1, and then a 2. And that was what? x2 tilde of minus m. What about x2 tilde of 1 minus m? That was our second try. So I'm going back to this slide, and we have it here. x2 tilde of 1 minus m was 2, 1, 0, minus 1. 2, 1, 0, minus 1. And if we can barely scrape that last one on here, let's see if it'll all fit. Not very well. x2 tilde of 2 minus m. And that was our slide here. x2 of 2 minus m was minus 1, 2, 1, 0. So minus 1, 2, 1, 0. And that's not particularly legible. But this is what we want to try to look at. Can we draw any conclusions from what's happening? This is x1 of m. That's the thing I like to think we hold constant. Here's x2 of minus m. And we got 1, 0, minus 1, 2. Then we shifted it by 1 to 1 minus m. And look what happens to the 2. The 2 shifts out and kind of shifts back in on this side. So it did shift, but it shifted in a modulo n fashion. And that's the key. The shift itself was periodic. The 2 goes out and comes around to the other side. And so what ended up happening? We had 2, 1, 0, minus 1. So these guys shifted forward, he shifted back. That was your 1 minus m. When we get into 2 minus m, what happened next? The 2 everything shifted forward again, and the minus 1 kind of shifted out, back around, and now it's kind of in this position here. So we got minus 1, 2, 1, 0. So in some sense, hopefully it's reminiscent of the chapter 2 material where things were sliding along linearly as they shifted. This one is periodically shifting. So it's just going in a circle. It's sort of rotating. So that's why they call this sometimes circular convolution. So now you could probably guess whoops, x2, what would be 3 minus m? What would that look like? Well, I can take this one and just shift it again. So now the 0 shifts from this position to here, and everything shifts down. So now that's minus 1, 2, 1. So now if we were going to calculate x2 of 3, we could simply go back up to our original sequence of x1 of m, which might be easy to just redraw that here so it's all on one page for completeness. So that one was what? That's also 0, 1, 2, minus 1. So this is our original sequence, and this is our shifted x2 of 3 minus m. So we just multiply these times each other. 0 times 0 plus 1 times minus 1, 2 times 2 plus 1 times minus 1. And so 0 plus minus 1 plus 4 minus 1 should give us 2. So let me see if I can get all this on one page. Our final output of this convolution, x tilde 3 of n, is what? I think we ended up with minus 4 was the first one, 2, 4, 2, and then dot, dot, dot because everything is periodic. So that was the output of the convolution. So hopefully kind of painstakingly going through those tables helps at least set up the problem so you can see kind of each step of the way. And then finally at the end you can see it's very similar to what we did before. It's now just a circular, kind of a circular shift to understand what's going on. So that takes us, we're done with periodic or circular convolution for the moment. And our next topic is basically tying all this together because we've spent a lot of time talking about the discrete Fourier series, or at least a lecture or so. Now how does this relate to the DFT? Because that's our main business. So our next subject is basically to tie these together and show that the DFT is really more of a process of using the discrete Fourier series in a certain way. So how is that way that we're using it? Well, we're going to start by connecting them, by kind of going back to our original equations and going from there. So if we start with our analysis equation, sort of as a reminder here, 2 pi n k over cap n, everything's periodic, that's our analysis. And then little xn is our, I guess we have 1 over n. This is our synthesis equation. E to the plus j2 pi n k all over cap n. Synthesis. Now what we're going to do is talk about how this relates to, I guess, the discrete Fourier transform. We're going to show how it works by relating it to the discrete time Fourier transform is going to be one of the tools. But I think the very first thing we got to do is show this identity that we're going to use. That's a useful identity that's going to be employed in all this. So those are our discrete Fourier series equations, which we already know. So let's talk about a common useful concept r equals minus infinity to infinity of this impulse train. This is going to play a key role. Periodic impulse train. Because when we use the DFT, we always use finite length sequences, and we do stuff and we get another finite length sequence. Well, it turns out, as we're going to show today, the discrete Fourier series is in there hidden, and the underlying periodicity doesn't go away if you even if you pretend it's not there, it's still there. As it turns out, this periodic impulse train kind of ties it together. So what does that look like? And hopefully that is not completely alien concept here. So at every could look like this for right, because r equals negative infinity to infinity. Make sure that's clear. So you can see it's just a bunch of impulses, or unit impulses separated by n. So what we're going to do to get this useful identity is say, well, let's apply the DFS to the periodic impulse train. If we do that, we get kind of an ugly expression. The n to n minus 1 that we always have for the analysis equation. Then we have our second summation due to the impulse train itself. Then we have the kernel here. And what, n equals 0, 1, 2, dot, 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 n minus 1. So the first order of business is, well, with an unit impulse in here, the good news about that is a lot of things are going to be 0, unless there's something very special about this argument, right? So n minus Rn has to be 0, or everything else is 0, right? But when is that the case? So we have to ask ourselves, when does n minus Rn equal 0? And at first it may seem a little bit complicated, but then you remember n can only be 0, 1, 2, up to n minus 1. So this can only go from 0 to n minus 1. And r can't be a fraction. R is another integer. So the only case is only when n equal r equals 0. So we're going to break it into 2 steps and let r equal 0 first and kind of see what falls out. So when r equals 0, things simplify a bit. So we've got n is 0 to n minus 1. Del n, because r equals 0, and we're e to the minus j 2 pi nk over cap n again. So we got rid of one of the summations. Now when n equals 0, that's going to get rid of the other summation. And so now we're kind of down to almost a trivial expression, where this is e to the minus j 2 pi n, but n equals 0. Make that a 0 times 0 times k over n. Put little multiplication signs in there so you can see that's 0. So all bets are off, or everything goes away. So x tilde of k equals 1 for k equals 0, 1, 2, dot, 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 n minus 1. So you can kind of see that was the periodic impulse train didn't turn out to be as boring as we might have thought, because that impulse train is the thing that creates the all ones output for the discrete Fourier series. So putting this together, we now have a discrete Fourier series pair that we're going to employ. So now we know, given this impulse train, we have a discrete Fourier series with the sequence 1. So we'll box this because we're going to reuse it. So we've got all ones. Let's go backwards now and say, well, what is x tilde of n if we reconstruct the sequence from all ones? And we're doing this kind of tongue-in-cheek, as you'll see. It's more of an almost rhetorical question. So we've got 0 to n minus 1. And we know how to, we know this is the synthesis equation, right? We're plugging this in here, e to the plus j 2 pi n k, all over cap n. So far so good. But xk is all ones. So what is that telling us? That's telling us that this is the situation. K equals 0 to n minus 1, e to the plus j 2 pi n k all over cap n. And that's what for k 0, 1, dot, 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 n minus 1. Now what we're going to conclude is we were doing this tongue-in-cheek because we already know what x tilde of n is. We already know what it is. We know that x tilde of n is this expression here. We took the Fourier series and got 1. So I'm going to say, yep, if I go backwards, it also has to be that. And so what do we conclude? We conclude that we have a new identity here that can sometimes come in handy of this impulse train equals a sum of these complex exponentials. E to the plus j 2 pi nk all over cap n. And so if you fell asleep for a second, you probably missed it, because it's pretty subtle how we took the discrete Fourier series of this, and we got 1, then we took the inverse discrete Fourier series, went backwards using synthesis, and then stopped and said, I know what it is already. It's the impulse train. So hey, look at this, a new identity. And we're going to set that aside. That's part of what we're going to need, tie it all back together. So with that out of the way, we're going to talk about how to tie it all together. And what ties it all together is the concept of sampling the Fourier transform. We've been sampling time signals, seems like the entire course, but now we're going to start sampling the Fourier transform and saying, now that I've got these frequency samples, what can I do with them and what happens? So to get started, we're going to use the DTFT, and we'll go step by step. We'll say xn is not periodic. I don't have the little tilde over it. And since it's not periodic, it has a discrete time, dtft, Fourier transform of x e to the j omega. So flashback to chapter 2. But now we're going to say, well, suppose just for analytical ease, and since we spent all this time messing with discrete Fourier series that require periodic functions or periodic sequences to use, let's just say that x of n is actually one period. It's just one period of a periodic sequence x of n. So kind of a clever reframe here. Since all my machinery works on periodic sequences, I'm going to say, well, x of n is really just one period out of this periodic x tilde of n. So what we're going to do is end up trying to sample the discrete time Fourier transform of x of n. So to get started, we already know the formula for the discrete time Fourier transform. So that's what, n equals 0 to n minus 1 x of n, and what, e to the minus j omega n. So we've got the Fourier transform. And we also know that x tilde of n actually does equal x of n with the fine print. Well, between 0 and n minus 1, it's the same, because x of n we know is not periodic. So what we could say is, well, that means, using this relationship, I know that x e to the j omega could be the summation, but since the summation goes from 0 to n minus 1, these are the same under those conditions. So I can make that substitution. And that's going to be good because this looks very similar to something we've been playing with all along, the analysis equation for the discrete Fourier series, right? So what is the analysis equation for the discrete Fourier series? Well, we've been calling that x tilde of k, and it's a summation from n equals 0 to n minus 1, very similar to what we have above. And oh yes, it works only on periodic signals, right? And now it's e to the minus j 2 pi nk all over cap n. And so I'm just going to write, this is our analysis equation for discrete Fourier series. So these are very similar. What would make them exactly the same? Well, if our frequency variable omega was samples of frequency, and we'll make the samples, well, how about 2 pi k over cap n samples? Maybe we should try that. What happens? They're going to look very similar. So let's put them all on the same page and say, let's let omega equal 2 pi k over cap n for the purposes of sampling. And so we end up with x e to the j omega when omega is sampled versions, or k is going to be 0 to n minus 1. That is the same, right? X tilde of n e to the minus j 2 pi nk all over cap n, which is the same as that. So this whole thing is telling us, hey, if we sample the discrete time Fourier transform, it really looks like the analysis equation or the discrete Fourier series sequence out of the DFS. So that's a good news. We can connect these two together. Sampling the discrete time Fourier transform basically looks like x tilde of k, discrete Fourier series coefficients. So far so good, but now can we work backwards? Can we actually synthesize x of n from those samples? And at first it seems like a trivial, oh, of course we can. We've already been doing it for the last 2 lectures. We can obviously synthesize the periodic version of x of n. That's the whole point of the discrete Fourier series. Well, we're not going just to just the periodic version. We care about the non-periodic version, and so that's where we're headed. So let's try it by going backwards and using the synthesis equation. So first of all, to get started, let's just get samples of a general sequence. We have some general sequence here, and I want to make that M. So XM is any sequence with an with a DETFT. We're trying to start general here. Any sequence with a discrete time Fourier transform. And there's really no length assumption on it at this point. And we said, well, let's go ahead and sample the DTFT of this general sequence. It's just any sequence with a discrete time Fourier transform. So we're going to sample it with omega equal to 2 pi k all over cap n. And we're going to take n samples. K equals 0, 1, 2, dot, 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 n minus 1. So kind of what you might think. We're going to take n samples of the DTFT spaced that way. And so that leaves us with e to the j, what, 2 pi k over cap n. So those are our samples of the DTFT. Is equal to what? M equals minus infinity to infinity. We had no length on this yet. E to the minus j 2 pi mk over cap n. So now we've got our samples. We've sampled the discrete time Fourier transform, and what we were trying to do is say, well, given those samples, can I get back? So let's try to get back. Can we get back? So to get back, we're going to apply what? The synthesis equation, right? So what was the synthesis equation? It was saying, well, given this periodic input Fourier series, that's what e to the plus j 2 pi nk, we can go backwards. And so let's just write this down as the synthesis. So this is from before, but now we're going to apply that to our sequence here and get something that looks a little ugly at first. So we've got 1 over n. We've got this summation, k equals 0 to n minus 1. That's part of our assumption. But now we've got to plug in this expression up here, equation 7. So that was what? That was our sequence of undetermined length. We took the discrete time Fourier transform of that sequence, and then we sampled it with n samples. And that was our 2 pi mk all over cap n. And then that whole thing is being put into our synthesis equation, so we've got another kernel of plus 2j. And that's, I think I want that to be 2 pi nk over cap n. And this was samples of DTFT. So the next step in any of these problems, it seems like, is interchange the order of summations and see what happens. If we do that, swoop them around, we can kind of move, let's move the infinite summation out front here, and since that's a function of m is a function of that, let's move it out. And so that leaves us with what? The other summation, which is 1 over n. And we've got a summation from k equals 0 to n minus 1. But now we've got these two kernels together, the m and the n. And so that's plus n minus m. So let's just write this all nice and easy as plus j 2 pi k all over cap n. But I have a plus n and a minus m, so that gives us this. So we're making progress, but now we're going to go back to our earlier slide and say, you know what, this summation of complex exponentials looks eerily familiar, because we went on what seemed like an off-roading excursion earlier in this lecture to compute this relationship. So now we can say, aha, this relationship here, or these sum of complex exponentials, looks very similar to that. So we're going to apply this, and that's going to turn out to simplify our lives. So I'm going to say apply identity, because where we're headed with this is it's going to make this whole thing look like a convolution. So that was what n minus r n was equal to the sum. K equals 0 to n minus 1 all over cap n. So we're going to apply that identity and simplify this just a bit. So that gives us our, still we have that summation. See if I can get everything on one screen so you can see what's happening. We still have that ugly summation there of m equals negative infinity to infinity. But now this is replaced with that, except there's one difference, right? We have n minus m here instead of n there. So let's make an adjustment to this expression. So now our infinite summation over r is the impulse, but now it's what? Instead of n, it's now n minus m minus r cap n. So now the next step is to say, wow, this looks a lot like a convolution. And we can make I think one more adjustment to it, make it hopefully stand out more. And we'll make this xm. And now I'm going to rewrite this. So the impulse is n minus r cap n minus m. So now it might look a little bit more like, okay, the summation from negative infinity to infinity, x of m. In the old days, that would have been, this whole thing would have been h, right? H of n minus m, something like that. Well, we have something very similar. It's this minus m. So we can rewrite this and say, you know what, I'm just going to make x of m convolved with that. It makes it even easier to see, I think. So we've got x tilde of n is what? It's x of n convolved with this impulse train that's separated by n samples. And our final maneuver is that we can simplify this. Convolving with delta functions is easy. It's always been easy. So we'll just go ahead and substitute x of n into that. And so the periodic version of x of n that we started with is what? It's an infinite summation of that one period of xn over and over and over again. So we've reconstituted it, but it's basically a summation of versions of the non-periodic, right? Copied over and over again. So what do we got here? The periodic version the periodic version of x of n, which we like to call x tilde of n, that is what results from applying the synthesis equation to samples of x e j omega. So a lot of words there. But I think what we're going to do is stop a little bit early today. We'll stop here, and next time we're basically going to take this through and apply this equation and kind of discover how sampling and frequency can result in aliasing in time, the opposite of what we've been doing, heretofore. So that's our next exciting topic, time aliasing, next time. So we'll stop here.
所以需要看看。